All right, so plan for the week, guys, is going to look like this. Today we're going to go over solubility because that's going to be part of our lab that we're going to do on Thursday. And we're going to go over the polar nature of water, which kind of is important for both this unit and the next. Kind of explains why water behaves differently than everything else. Like if there's a rule, water's the exception to it. Okay. And we're also going to look at this week, so we'll have tomorrow, we'll have our usual Tuesday quiz, then we'll have the Chromebooks and we'll do the pre-lab, okay, for the labs that we're going to do on Thursday. Wednesday, we'll kind of maybe finish that up and start looking at some other stuff like reactions. Thursday we'll do the lab, and Friday we'll start reactions, okay, and then you have a week off. All right, so if you are going to be away, okay, Thursday or Friday, because I've been like getting a lot of emails about people who are leaving Thursday, then you won't be here for the lab. And there's an observations video for the lab. It's me doing the lab. So you'll have to watch that and record the observations from the video, okay, and then do your analysis and all of that kind of stuff. Okay, the lab will be due not obviously the day after the break, okay, I think I'm going to do for like the Wednesday or something like that. So you've got time to come in and see me, ask questions, have me review your lab, okay, the stuff we've talked about before. Okay, questions? All right. Okay, so for today, okay, we're going to review terminology related to solubility. So some of that stuff is going to probably sound familiar to you. You've probably learned about, you know, like homogeneous, heterogeneous, mechanical mixtures, okay, those kinds of things. Understand what is meant by the term polar molecule. Okay, water is a polar molecule. I did briefly touch on that when we were talking about molecular bonds and how they share electrons, but it's not always shared. Remember I said it was like the friend who, when you order pizza, eats 6 out of the 8 pieces. Okay, so we're going to talk about that. Okay, and also look at, because it's a polar molecule, water has many important and unique properties that make life on Earth possible. So we'll talk quite a bit about water and its polar nature, and then after that we'll have a little bit of time to work on some more naming stuff. Okay. So not everything dissolves equally well, okay? You've probably realized this if you've ever tried, you know, if you've ever done any cooking or baking, okay? Some things dissolve really easily, like salt and sugar, and some things dissolve very poorly, okay, like cornstarch, which doesn't really dissolve at all, okay, and things like that, okay? So the degree to which something dissolves in something else is called its solubility. Typically, we rate solubility as the ability of something to dissolve in water. Okay, water is the quote-unquote universal solvent, okay, which is sort of odd because lots of things don't dissolve in it. But we typically rate things solubility based on how well they dissolve in water. Okay, so a substance is said to be insoluble if it will not dissolve in another substance. Okay, so insoluble, okay, that's an important piece of terminology right there. If something is insoluble, it will not dissolve in something else. So oil is insoluble in water. Okay? It doesn't matter how much you stir it, you can get it suspended, but it'll eventually all come to the top again. Okay? It is not going to dissolve in water. Okay? If a substance remains insoluble and in a solid form, then it is called a precipitate. Okay, so the two terms important from that slide are insoluble and precipitate. Okay. Those terms sounded familiar so far, Jimmy? Now I'm going to show you kind of what a precipitate looks like here. I have this, like, well, the video is really good, but it has this incredibly odd Italian guitar music in it. I don't know why they picked this music for the video, but it's like completely out of place. Okay, it would be like, you know, watching the intro to Star Wars, but there's like blues music playing instead. Like it's kind of like that out of place. Okay. So, other terminology here, guys. A solution, okay, is any mixture that contains a solute dissolved in a solvent. Okay, so a solute is the thing being dissolved, the solvent is the thing doing the dissolving. That's why we often call cleaning agents like Pine Sol or Mr. Clean or CLR, okay, or something like that. We often refer to those as solvents. They help us to dissolve the crud that we're trying to get off of, the inside of the shower or inside of the toilet bowl or whatever. Okay, they help us to dissolve that. Solvents are things that do the dissolving. Solutes are the things that dissolve. Okay. The other term for that is a homogeneous mixture, and I will use those terms interchangeably. Solution with homogeneous mixture. Okay. Now, what does the prefix homo mean? The same or one. Okay, one or the same. Okay, that's what the prefix homo means. So if something is homogeneous, then it's all one part. Okay, like the mixture we see here on the left. Okay, that would be a homogeneous mixture. It has only one visible part. Okay, so things like Gatorade are a homogeneous mixture. Okay, coffee, okay, if you don't put other things in it, is a homogeneous mixture. Okay, everybody with me so far? All right. Now, if something is a heterogeneous mixture, hetero means many. Okay, so many parts. Okay, this is something that stuff is not dissolving in. That's the picture on the right. Okay, so that would be oil and water. Or if I mixed iron filings in sand. Or, when you go to Subway and they're asked, do you want salt and pepper? And they only pull out one shaker. Okay, because it has both in it for whatever reason. Okay, it's all one. It's not one part. They're mixed together, but I can easily separate them. Okay, making sense? Like if I have that heterogeneous mixture there, could I get the other stuff out by simply filtering it? I could. If I filtered this, would the stuff come out? I wouldn't. Okay, it's one visible part now. I can't get that part out by filtering it. Okay, if I wanted to get that other stuff out, I'd have to basically evaporate all the water, so it would be left behind. Okay, if I had iron filings and sand mixed together, how would I separate them? Use a magnet. Stir it with a magnet. Okay, if you had like a container that had iron filings and sand, just put a magnet in there, stir it around, and have all the iron filings attached to the magnet. There's always a mechanical way to separate a mechanical mixture. Right? A homogeneous mixture or solution has to be separated using the physical properties like solubility or like boiling point or something like that to get rid of them. Okay, questions there? Everyone okay with that? All right. Okay, other definitions here. Solute, like we said, that's the substance being dissolved. Okay, and solvent is any substance that will dissolve another substance, like salt in water. Okay, well, water is the solvent because it's doing the dissolving. Salt is the solute because it's the thing being dissolved. Okay, is that ringing a bell for everybody? Okay, hopefully so. Is that the kind of thing that might end up on, let's say, I don't know, Thursday's quiz? Definitely could have solubility terminology in it. Not tomorrow's quiz. We already talked about, there's the thing I was looking for. Okay, precipitate. Any solid which is produced in a reaction and will not dissolve in solution. One of the reactions, let's see, two of the reactions we're going to do in our reactions lab are going to produce a precipitate. That is, we're going to mix two clear solutions together. And when we do that, a solid will form. Okay? And it'll fall out of the solution. Okay? And that's where the name precipitate comes from. Okay? When I mix these two things together, the solid falls out of the solution and collects on the bottom like precipitation. Okay? It means precipitation literally means to fall out of. Okay? So if I mix two things together, okay, I might get a precipitate like this, right? And I'm going to show you the video where they mix two things together and that happens. Now that you feel all melancholy because of that, like really melancholic Italian guitar music. Okay, so you can see clearly that there was a solid that formed when that mixture was poured in there, okay, it got all cloudy, okay, and that would have eventually precipitated out to the bottom. Okay? Sometimes it precipitates barely noticeable, and other times you can't miss it. Okay? So in that case there, it was one of those ones where you really can't miss it. All right, and then the definition of solubility, okay, it's the degree to which a substance will dissolve in another substance, okay? That's an important definition. It is one of those physical properties we're going to test in the lab on Thursday, okay? It's one of the tests that we're running. So how much solute can go into solution before the solvent becomes, and then this is another important term, saturated. Okay? If something is saturated, it can hold no more. Okay? We usually use that term when we're talking about how wet something is. Okay? You know, if you drop a washcloth in the sink and it's full of water, you pull the washcloth out, it's saturated. It can't hold any more water. Okay? But solutions can become saturated as well when they won't dissolve any more of what you're adding to them. Okay? Now, on that note, there are some things that can affect solubility. Okay? Like agitation. Can you get more stuff to dissolve if you agitate it? Like shake it or stir it? Definitely. Okay? Basically what you're doing is creating more spaces for that material to dissolve between the water molecules. Okay? Or you can heat it up. Because heating it up basically does the same thing. It makes the water molecules move more quickly, okay, which increases the degree to which things can slip in between them, okay, and get dissolved. Okay? Now, some things should be soluble, some things should not. Like Twinkies. Okay? The modern Twinkie is less about pastry and more about science. Okay? A Twinkie is supposed to be cake with like a cream filling. That's what the original Twinkie was. The modern Twinkie is not that anymore. Okay? If you take cake and you put it in water, does it dissolve? I had cake yesterday. It doesn't dissolve. Okay? It won't dissolve in water. That's part of the problem when you're doing the dishes afterwards. Cake doesn't dissolve in water. Okay? Twinkies do. Here's the good side of that. If you ever break your jaw and you like Twinkies and your jaw wired shut, you can just put them in a glass of water and then drink the Twinkie. I don't know if it tastes quite the same, but okay, you can do that. Right? Because over time, the Twinkie has been altered. The recipe is no longer anywhere close to what it used to be. Okay? The original Twinkie had a shelf life of about a week because it was made of real things like eggs and milk, okay, and butter and flour and sugar. Okay? But that doesn't last long. Okay? You leave that, out and mold will start to grow, bacteria will start to grow, and it will spoil. That's not good if you're trying to make money on selling Twinkies if a whole bunch of them go bad before they get sold. So, the makers of the Twinkie, Hostess, okay, started tweaking the recipe to increase the shelf life of the Twinkie. And then World War II came along and there were shortages to their ingredients. Okay? The original Twinkie actually had banana cream filling. Okay? But there was a banana shortage during the war because lots of shipping was being used to ship, well, war material, okay, as opposed to food. So they had to change the recipe again. Okay? It became more of like a light, almost vanilla cream. Okay? And they stopped using the natural ingredients like eggs. Okay? They used like a protein substitute. They used powdered milk. Okay? Or now it's also called modified milk ingredients, which means it's not milk at all. It's like something else entirely. Okay? No more butter. Okay? They would use like non-hydrogenated vegetable oils. Okay? Things that last a lot longer. And then they would add preservatives. Okay? Things that inhibit the growth of bacteria and mold. The modern Twinkie has a shelf life of like over a year. Okay? It can last a very long time. Right? But the original Twinkie had eggs in it. That's what gave the Twinkie its characteristic yellow color. As soon as they substituted in the protein substitute, the color changed. And the Twinkie looked like it was made out of drywall. It was gray. For some reason, nobody wanted to eat it anymore. Okay? It went from looking like real food to like gray and gross. Okay, so they added something in to make up for the color. Anyone know what they added in? What they added in is actually banned as a food product in most parts of the world except North America. Yellow dye number 5. Okay? Yellow dye number 5 is put into Twinkies to give them their yellow color. It's highly soluble in water and it's a known carcinogen. Means it causes cancer, but it's in there. Okay? Because, well, you know, as long as you don't eat 12 Twinkies a day every day, you're probably going to be fine. Okay? So, if you put a Twinkie in water, that's what will happen. It will dissolve. Because it no longer has any of those natural ingredients in it. Because butter is not soluble in water. Okay? Eggs aren't soluble in water. Okay? All of that stuff. Yeah? I'm not trying to say you got to eat organic or anything like that, because I'm like, I would be totally hypocritical if I was saying that. Okay? But know that we've modified lots of things. Okay? And as a result, we've changed a lot of what maybe they should be. Okay, I need you all to take out your periodic table. Of course, you're going to need one. Okay, so on the back of your periodic table is this chart. This is your solubility chart. It allows you to determine whether a substance is soluble or not in water. Okay, so here's how it works. Okay, on the top row, you have your negatively charged ions, with the exception of ammonium, which is up there as well. Okay, you have your negatively charged ions. And then the rest of the chart is about what metals they are with. Okay? So if I was asked to determine whether, let's say, sodium chloride was soluble, this is what I would do. I would find chlorine on the first row because it's the negatively charged part of that compound. Okay? So chlorine is right here. It says, okay, according to the chart, that everything in the first row is soluble and everything in the second row is not. Okay, I know it says solubility less than, it says slightly soluble. You can say not. Everything in the second row is not soluble. Okay, everything in the first row is very soluble. So I see chlorine is here, and it says that chlorine is soluble with most things. Gosh, that's helpful. Okay, what does most mean? Most means more than half? Yay. Okay, it doesn't really help me determine whether this stuff is, whether sodium chloride is soluble. So what I've got to do is I've got to go down into the next row and make sure that sodium is not in amongst the things that are not soluble. Okay, so what I see down there is that chlorine is not soluble with copper 1, silver, mercury 2, lead 2, or tantalum. Okay, which means then that since sodium's not there, sodium chloride must be soluble or not? Soluble. We know that's common sense. We've dissolved salt in water before. Okay, sodium chloride would be soluble. All right, what if I had this stuff? What if I had lead 2 sulfate? Okay, well, I do the same thing. I find the negatively charged part of it. It's right here. It says it's soluble with most things, but not with calcium, strontium, barium, silver, mercury, or lead. Okay, so that stuff would not be soluble. If I put that in water, it would not dissolve. Okay, everybody all right with how that chart works? Okay, so you look up the non-metal basically, or the negatively charged polyatomic ion, if that's the case, in the top row, and then you look to see is what it's with in the first row. If it is, it's soluble. If it's in the second row, it's not. All right, I want you guys to try those 8. Just right beside them, S for soluble, NS for not soluble, but also write down the questions. Okay, so you've got some in your notes, okay, to refer back to. All right, I'll give you a couple minutes on that, and then we'll go through them together. Okay, so for our first one there, we got calcium sulfate. So we find sulfate, it's right here, okay, and then it says it's soluble with most things, but I see calcium down here in the not soluble row, okay, so calcium sulfate would be not soluble. All right, for potassium hydroxide, okay, I see hydroxide is here, and it says group 1 ions. Where's group 1? Right here, under the big 1. That's group 1. So that means it's soluble with everything in that row. Is potassium in that row? Okay, so that stuff is soluble. All right, and then lead 2 chloride. All right, so I find chlorine, it's right here, soluble with most things, but we see lead down here, okay, particularly the lead 2 variety, okay, so that stuff would be not soluble as it is in the second not soluble row. All right, then tin 4 fluoride. All right, so here's fluorine, soluble with most things, but not these things. And I don't see SN in that row, so is SN part of most then? Yep, must be. All right, so this stuff would be soluble. All right, for copper 2 sulfate, okay, sulfate is right here, soluble with most things. I don't see Cu down in this row here, so that stuff must be soluble. Copper must be part of most. Okay, for potassium bromide, okay, I see bromine right here, same one as chlorine is in, okay, soluble with most things. I do not see potassium here in the not soluble row, so that one would be soluble. Okay, sodium fluoride, so fluorine is right here. Sorry, it's not sodium, silver fluoride. Okay, fluorine is right here, soluble with most things, but I don't see silver anywhere down here, so that stuff is soluble. Okay, and then beryllium nitrate. Nitrate's right here, and nitrates, guys, are basically soluble with everything. Okay, so if you've got something nitrate, it's probably soluble, because the only thing nitrate's not soluble with are these things that I don't even know the name of. Okay, like I've never ever seen any of those ions anywhere but this table here. Okay, so basically everything is soluble, or nitrate, anything nitrate is going to be soluble. All right, is that pretty easy to use? Okay, here's where you're going to be asked to use that. On a test, I say, which of the following compounds is soluble? A, B, C, or D, and you got to figure out which one using your chart. Okay, or when we do our reactions lab, okay, one of the analysis questions says, in your lab, 2 of the reactions produce precipitates. Okay, according to the reactions you wrote, which product was the precipitate? So basically you got to look at your products and figure out which one of them's not soluble. That one would be the precipitate. Okay, so a couple of situations, but in the end, they are all done the same way. I grab this chart, I look at which row the thing is in, and I determine whether it is soluble or not. Okay? Could that be on Thursday's quiz? Definitely. All right, any questions about the solubility chart? Okay. Then, let's talk about water. Okay, so water, even though it starts with a metal, hydrogen, okay, is a molecular compound. There's like exception number 1 for water. Okay, it's a metal and a non-metal, but it's not. Okay, so water is a molecular compound, which means it shares the electrons in a molecular or covalent bond. The problem with water is that the sharing's not equal. The hydrogen, the electrons that are from the hydrogen spend more time close to oxygen than they do close to hydrogen. Okay? And what that ends up doing is making one side of the molecule look negative and one side of the molecule look positive. Okay? That's why we call it a polar molecule. One end is different than the other. Like the world has a north and a south pole. They are different from each other. Okay? All right, so we discussed earlier in the unit, atoms of different elements can form compounds. Electrons can be gained or lost if it's ionic, but in a molecular compound, they get shared. Okay, so if I'm looking at this water molecule here, okay, I've got my oxygen atom, okay, and it's going to have its 8 electrons, okay, 2 in that first shell, and then 6 in the outer shell, and then it's going to share the 2 electrons from the 2 hydrogen atoms. Okay, now those electrons don't just sit there. Okay, we know electrons move around. Okay, they're trying to orbit the nucleus of the atom that they're part of. Okay, but what happens in a covalent bond is the orbits actually get altered. They often get stretched. Okay, in the same way that if, like, let's say a black hole were to come into our solar system, would it change the orbits of the planets? Okay. Would the planets be attracted to the big giant black hole that is massive compared to the sun? Okay. Certainly would. It would stretch out the orbits. The planets would probably stop orbiting the sun, in fact, okay, and go towards the black hole. Well, in a polar molecule, a similar thing happens. The electrons are going to hang around the thing that holds them tighter. Okay? And how hard or how tightly an element holds on to electrons is based on one of its physical properties. And that physical property is electronegativity. Okay? Electronegativity is actually one of the things listed on the periodic table. Okay? So if you look at your periodic table, underneath the atomic number, okay, is another number. That's the electronegativity of that particular element. The higher that number is, the more strongly or more tightly they hold electrons. Okay? Hydrogen actually has a reasonably high electronegativity, especially for a metal, right? But oxygen's is even greater at 3.4 versus 2.2. Okay? Because of that, hydrogen's electrons hang out near oxygen more. Okay? And when that happens, what you end up getting is 2 hydrogen atoms on the top of the molecule whose nucleus is made of 1 proton. And that proton is essentially sticking out, making that end of the molecule look positive. Meanwhile, the bottom of the molecule is where the electrons are hanging out. So that end looks negative. Okay, everybody with me so far? Okay, because this is part of what you need to know about a polar molecule. Okay, in a polar molecule, electrons are not shared equally because of the electronegativity of the various atoms. That makes the molecule look charged, even when it's not. Okay, that's the first part of explaining what it means to be a polar molecule. Okay, so the sharing's not always equal. Okay, some elements are more electronegative than others. Okay, and so this is what we end up getting. Okay, we get a polar bond where the electrons don't get shared equally. Okay, we end up with positive ends and negative ends. Right? Now, if I put a positive and a negative near each other, what will they do? They'll attract each other. Opposites attract. Okay? When you get polar molecules together, and they've got one end that's positive and one end that's negative, the ends that are opposite attract the ends of other molecules that are opposite. Okay? And so, water can do some things that other compounds can't, like exhibit surface tension. Okay? Some people know what I mean by surface tension. Okay? Like that meniscus. You never notice you can fill a glass slightly more than full with water? Okay? Or why you can skip a rock across a lake? Okay, that's because of surface tension. Okay? Or if you see like a bead of like dew or something like that, and it's on the leaf of a plant, okay, and it just beads up and then it runs off. Okay, all of that has to do with these polar bonds, or what we call hydrogen bonds, okay, between polar molecules. Right? So when you have a whole bunch of polar molecules together, okay, they will form bonds between them. If that bond involves hydrogen, it's called, oddly enough, a hydrogen bond. Okay. The same thing can happen, not just between water molecules, but between water and another polar molecule. So you can actually see it with, if you have like a really cold drink in a glass on a hot, humid day, okay? You start getting the condensation on the outside of the glass, okay? But the water, like the beads of water can actually get pretty big before they run down the side of the glass, okay? Or after a rainstorm, if somebody's just waxed their car, the beads of water can get pretty big before they run off of the car, okay? That has to do with surface tension, with the hydrogen bonds. They bond not only to each other, but they can also bond to the wax on the surface of the car, okay? Or the side of the glass, or the wax on the cuticle of the plant's leaf, okay? Or anywhere else. Okay? Is that making sense? You guys kind of have seen these things in your life before? All right. Okay, so the water molecule ends up being shaped kind of like Mickey Mouse. Okay, got the two ears on the top, okay, and they're 90 degrees apart. Okay, so it's shaped like a right angle, right? And so, as a result, water can actually bond to 4 other water molecules because it's got 2 parts that are positive and 2 parts that are negative. Right? And so it can form a hydrogen bond to this water molecule, a hydrogen bond to this water molecule, to this one, to this one. That's what creates that surface tension or that meniscus. Okay. Now, are those bonds easily broken? Like if you have like a glass that's slightly more than full, if you touch it, is it done? Yeah, you break those bonds easily. Hydrogen bonds break very easily, but they also reform very easily. Okay, so that surface tension, the hydrogen bonding is kind of, let's say not really super strong, but also super quick to come back. Okay, so that causes some of the anomalous properties of water. One of those is that water, unlike basically everything else, expands when it freezes. Okay, you probably noticed this if you've ever frozen a water bottle, right? The bottom of it pops out. Okay, and then you can't sit it on the counter, it falls over, okay, because the bottom's popped out. Okay, so that's because water, as it cools, does what everything else does. It contracts, takes up less space, until it gets to about 4 degrees Celsius. At 4 degrees Celsius, you're now trying to push those water molecules closer together than they would like to be. And because they're polar and charged, what you end up doing is putting too many of the negative ends too close together. And if I put 2 negatives together, instead of attracting, they'll repel. Okay? So as the temperature drops between 4 and 0, where the water would freeze, the water actually rebounds, okay, and expands outwards and ends up taking up more space than its liquid counterpart. Right? So ice is less dense than liquid water, right? That's why ice cubes float when you put them in water. They're lighter than water. They're made of the same stuff, okay? But because their molecules are further apart, they're less dense and they float. This is one of those things that's crucial to life on Earth. If ice was like everything else, okay, and as meaning solid water being more dense than its liquid counterpart, lakes would freeze from the bottom up, which means in the wintertime here in Canada, lakes would be frozen solid all the way to the bottom. And it is because ice is lighter than water, right, that the lakes don't freeze all the way to the bottom. Okay? The ice sits on the top and actually provides an insulating layer between the outside air and the water below. Okay? That preserves life in cold places. Okay? Making sense? All right, so this is kind of a picture of that idea, what happens to water when it freezes. Okay, this is liquid water. You can see the molecules are really close together. Okay, this is ice. Forms a crystalline structure because the molecules get forced a fixed distance apart, okay, creating those crystals. Okay, here's the other thing that the polar nature of water provides, okay, that's important for life on Earth. It provides a means for plants to transport water without the expenditure of energy. Okay, so like a giant redwood in the forest, to take water from its roots to its leaves at the top of the tree, which could be over 100 meters up from the ground, requires no energy whatsoever. Because water is polar and bonds to itself, it can be pulled as a single unit up the tree. Okay? So what happens is, as water evaporates from the leaves, okay, it's bonded to other water molecules below. So as one water molecule evaporates, it pulls on the other water molecules that are below. Okay? Anyone ever play with a barrel of monkeys as a kid? And those monkeys with hooked hands? It's kind of like that. You can make a long chain of monkeys if you hook their hands together. Okay? Well, water does the same thing. It hooks to itself with a hydrogen bond. So when one water molecule goes up, it pulls on the one below, which is attached to the one below, which is attached to the one below, okay, and pulls it up the tree. Okay? It's that polar nature of water, that hydrogen bond, that allows for that to happen. Okay? The hydrogen bonds can also happen between the water molecules and the inside of the tubes in the tree. Okay? So they can stick to the tree, they can stick to each other, okay? And up the tree they will go. Okay? If water was not a polar molecule, plants would not be able to transport it up from the roots to the leaves. Right? So it looks kind of like this. Okay? So inside of the xylem tubes, those are the tubes that transport water, okay? You've got water molecules that create a hydrogen bond with each other. Incidentally, that's called cohesion, okay, when they bond to each other, okay? And they'll bond to the inside of the tree. Incidentally, that's called adhesion, and you do need to know those two terms. Okay? So a hydrogen bond with something like yourself, so water to water, is cohesion. A hydrogen bond with a different polar molecule is adhesion. Okay, so this process only works, though, if the tubes are tiny. Okay? Is water fairly heavy? So you can't have a tube like this, okay, and hope for this process to work. A tube that's this diameter. You couldn't even have a tube that's the same diameter as this pen. It wouldn't work, okay? Because there'd be all this water in the middle of it that can't attach to anything else. It would be too heavy and it wouldn't support it. The hydrogen bonds are too weak. It would break. Okay? You can think of it this way. If you've ever tried to drink with a really, really thin straw versus a really, really big straw, it's much easier to pull water up a little straw than a big straw, because the column of water in the middle is not big. So the properties of the polar nature of water works for you in a small straw with a small diameter, okay, versus a straw with a big diameter. Okay? Like if you were trying to draw water vertically upward in a big round pipe, okay, that would be much more difficult than if you had a bunch of small ones. Okay? And that's what a tree does. The little tubes inside the tree are only a few micrometers across. Okay? They're microscopic, but there's millions of them. Okay? All right, I think we will leave it there. This is just some examples here. Okay, apparently you're able to do this. I tried for an entire afternoon and I failed, but apparently you can do that. Okay, the meniscus, those hydrogen bonds, okay, are apparently strong enough to support a paperclip, but I couldn't do it. Okay, because the hydrogen bonds are also really weak, and if you disrupt them at all, like poking them with the sharp edges of the paperclip, okay, it just breaks. Okay, this is what I was talking about here, the water beads on the leaf of a plant or on the hood of a freshly waxed car, okay, or something like that. And there's even animals that use this. Okay, lots of insects can float along on the surface film of the water on a river or a lake, okay, because of that polar nature of water. They're not heavy enough to break it. Okay, they've got their weight spread out over a wide area, so they can float along. Or you could have the Jesus lizard, okay, that can run across, okay, a lake or a stream or something like that. Okay, all using the polar nature of water. So here's how I'm going to ask this on test. I'm going to ask you to explain to me what a polar molecule is. You're going to have to tell me, okay, about the non-equal sharing of electrons. You're going to have to tell me what that does to the molecule, make charged ends, positive and negative. Okay, what those charged ends can do, well, they can hydrogen bond to other charged polar molecules, okay, creating cohesion, adhesion, okay, which would make surface tension, which would allow plants to draw water up a tree, or a Jesus lizard to run across a lake, okay, or something along those lines. That's what you're going to be asked to do. Okay, all right, I'm going to give you 5 minutes here to answer all the snaps you got while I was talking. Okay, give you a little break, and then we're going to do a bit more naming stuff here. All right, so our first one there, do we have an ionic compound or molecular compound? It's ionic. Potassium's a metal, and we have a polyatomic ion in there. Okay, so this will be, I write the name of the metal, I write the name of the nonmetal, in this case the polyatomic ion, carbonate. Okay, potassium carbonate is the name for that. Okay. And for number 2, I've got copper and I've got sulfur. Ionic or molecular? Ionic, okay. Does copper need a Roman numeral? Okay, so I'm going to go copper. Then I'm going to write the name of the nonmetal, but I'm going to change its ending to "-ide". Okay, so I've got essentially the name, but now I've got to figure out what charge does copper have on it. All right, so I look to the nonmetal. Sulfur is always a -2, so that means I need to get 2 negative charges out of, or sorry, 2 positive charges out of 2 copper atoms. That means the charge on each copper must be 1, right? Because 2 divided by 2 is 1. All right, so this is copper 1 sulfide. All right, the third one, I've got nitrogen and fluorine. Are those both nonmetals? Okay, so what kind of compound is this? It's molecular. Okay, 2 nonmetals, so now I need prefixes. Trinitrogen. Okay, penta for 5, fluoride. Okay, and then for number 4, I've got iron and sulfate. Okay, ionic compound, and iron has more than one possible charge. So I'll write the name of the metal, iron, write the name of the nonmetal, sulfate. Okay, and now I've got to figure out what's the charge on iron so I know what Roman numeral to use. Okay, charge on sulfate is always -2. There's only one sulfate here, so that means I've got to get 2 positive charges from 1 iron, so the charge on iron is 2. Iron 2 sulfate. All right, and number 5. Got 2 carbons and 6 hydrogens. Okay, both nonmetals? They are, because hydrogen is listed second. Okay, so that makes this a molecular compound. So we would have dicarbon, okay, hexahydride. Okay, questions on any of those? All right. And then for number 6, okay, we got to do the formulas here. Disilicone heptachloride. Okay, if I got prefixes, then I know I've got a molecular compound. Disilicone means 2. Heptachloride means 7. Okay. All right, for number 7, cobalt 2 bromide. Okay, so I've got cobalt. What does the Roman numeral tell me about the cobalt? +2 charge. Okay, and it's with bromine. That is a -1 charge, so drop and swap. COBr2. Okay, for number 8, that's a tricky one. Ammonium, what's that? All right, it has a positive charge. It's that only positively charged polyatomic ion, NH4, and it is with nitride. Okay, nitrogen's always a -3. Ammonium is always a +1. What am I going to need around the ammonium? Brackets. Where does the 3 go? Inside or outside? Outside. Okay, so you would have NH3, or sorry, NH4, 3, N. Okay. All right, and then for number 9, we got manganese 4 nitrate. Okay, manganese is Mn, and the Roman numeral tells me it's the 4 plus kind. It is with nitrate, NO3 with a -1 charge, drop and swap. Okay, the 1 goes here, but we don't write those. Brackets with a 4. Okay, and then our last one, also ionic, lithium +1, permanganate, MnO4 -1. Those are good the way they are, LiMnO4. Okay, some stuff about the lab. First off, lab safety stuff. When we are in the lab on Thursday, your safety goggles will be on all the time, okay? First thing you do when you walk into the lab, okay, is you go to the lab station, and in the top drawer of all the lab stations, there will be safety goggles, okay? Put them on. If you are already wearing prescription glasses, you will need the large variety of protective goggle that will go over your glasses, okay? Because the goggles need to keep stuff from going in the top or in the bottom or something like that, okay? If you have a set of contacts, I find the best thing to do on lab day is to wear contacts, and then you can use the much lighter and less likely to leave goggle marks on your face goggles, okay? Now, this is the correct position for safety goggles. This is not, okay? They are not a forehead protector. They are not a protector, they go here, right? They are on at all times. I cannot stress that enough. I do not want to have to put anybody's face in the eye wash station. It never ends well, okay? The last time I had to do it, both people ended up bloodied. And I was one of them, okay? Because you get something in your eye, and you're going to flail and scream. I don't care how tough you think you are, okay? You're going to flail and scream, and I'm going to have to grab you, and I'm going to have to take you over to the lab, to the eye wash station, and you're going to fight me, okay? Not because you don't like me, maybe, okay? But because you're hurting, okay? And I'm going to try and peel back your eyelids, okay, so that the water goes in your eyes, okay? And you're going to flail. And it's going to be very bad, okay? Like I say, the last time it happened, the person was flailing so bad, they swatted backwards and got me right on the bridge of the nose, okay? And so I'm leaking, and then I was choked. And grabbed them by the hair and put them into the lab, into the eye wash station, which has a metal bar that goes right here, so they got it right in the middle of the nose. Yeah, it didn't end well, okay? Both people bleeding. So I don't want to have to do that. So keep your goggles on. I'll be really sticky about it, okay? There are aprons as well. They're on the right-hand side when you walk into the lab. You can put those on or not. That's totally up to you, okay? But I would not wear your like tuxedo or grad gown or anything like that into the lab, okay? Don't wear your favorite, hoodie or whatever. You need to be wearing clothes that if you got something on them, you wouldn't miss them. Okay, on the note of hoodies and such, if you have drawstrings that hang down from the hoodie, they need to be tied up and tucked away as best possible, okay? Anything that can hang down and get into the lab needs to be tied back. So if you have long hair, I suggest you put a hair tie in your science binder, okay? So that you always have a hair tie with you, okay? So that you can tie your hair back for the lab, okay? Loose clothing, okay? So if you're wearing like a jacket, okay, or a heavy sweater or something like that, that can, go forwards, you're gonna have to take that off for the lab. Okay? Footwear, not that it's going to be a problem in winter, okay? But you can't have anything that's open on the top, like sandals or flip-flops or anything like that. You have to have shoes that actually cover your feet. If anything was to spill off the edge of the lab station, the first place it'll go is on your feet. And if you don't have some shoes on, there's not that extra layer of protection for your feet. Okay? Plus, in the lab, sometimes stuff that's made of glass gets dropped and broken, and then there's glass everywhere. So, okay, better to have real shoes in the lab. Okay? When we are in the lab, there is also no horseplay of any kind. There is zero tolerance for that. I will not warn you. I feel like you should listen to this. Okay? I will not warn you. If you horse around in my lab, you're out. okay? It is not a 3 strikes rule. You're out. If I catch you horsing around in my lab, I do not take chances with people's safety, okay? The stuff that we are going to be using in the lab for our lab on Thursday, okay? The first piece of equipment is this little thing. This is a depression plate, okay? Not because it's sad, okay, but because it's got depressions in it, dips that you can put stuff in. All right, so that is what we'll be putting the unknown compounds in order to perform the tests on them. Okay, the depressions are reasonably deep and will allow us to put enough water in there to perform the solubility test and conductivity test and all that stuff. So that's the first piece of equipment. Okay, second piece of equipment is this prison shank. Scupula. I don't know why they got these. These are brand new this year, and am I wrong? That looks like a prison shank, right? Yeah, okay. So it's a scoop, the lab scoop. Okay, you're going to find them in each of the unknown compounds. They're for transferring the compound to your depression plate. Okay, they hold the stuff quite nicely. Okay, that's what they would be used for. Okay, a thermometer. You might call it a thermometer. Okay, you're going to be taking the temperature during the solubility test. Okay, that is what this is for. It is not for stirring. Okay, it is simply for measuring. You will get a separate, oddly enough, glass stirring rod, okay, to do the stirring with. We use glass simply because it can't leave anything in the solution. It doesn't dissolve or get soggy or do anything like that. Okay, so this will be in there. What's the little red plastic or rubber? Actually, it's rubber thing for it. Actually, and that's the most common thing, because that's logically what we would do with it, but actually its purpose is not logical. It is to insulate the thermometer against the heat of your fingers. Okay, so you should hold the thermometer by that little rubber mark. Well, it's not a marker. Okay, it's by this little rubber thing to keep the heat of your fingers from interfering with your temperature reading. Because if you hold the thermometer like this, it's going to get hotter from the heat of your own body, okay, and interfere with your temperature reading. So that's actually what those are for. You'll find if you're trying to mark with them, they'll actually kind of get in the way. Okay, so just for holding the thermometer with. Okay. All right, and then your conductivity apparatus. Okay, so this is a conductivity tester. The 2 leads have to go in the solution that you wish to test. There's a little button on the side. When you press it, the on light comes on, okay, to let you know that it's actually working. If that light doesn't come on, you need to bring it back to me, okay? And you'll be testing the conductivity of the solutions in what is hopefully a cleaner depression plate than that one, okay, by simply putting some you'll have your solution in there already, okay? So, put the water in there, okay, you put the conductivity tester in, and you press the button. So clearly, it's not only tap water, but this is not clean either, okay? Because what should distilled water read on here? Should read 0, okay? This is reading like 5, okay? So there's definitely stuff in there. And if I were to do this, and add some more ionic compound to it, okay, we can see that the conductivity went up because I put more available positive and negatively charged particles in there, okay, for it to conduct electricity with. Okay, so you'll have that. Pretty simple to use. And the last thing, Hydrion paper, pH paper. All right, there's a color code on the side. Okay, so you simply take a piece of it out. Okay, there's usually 2 groups of it in there. 1 piece of Hydrion paper should test 2 solutions. Okay, so you just tear a piece off, rip it in half. Okay, we'll save materials. Dip it in. All right, give it a minute to change color, and then compare. And somewhere between 6 and 7. I got a little bit of green in there, so 6.5. Okay, which would be logical for, water with salt in it. Okay, everybody with me on that? Okay, pretty easy to use, pretty straightforward. Okay, so tomorrow we'll have the Chromebooks. After your quiz, okay, we will start the pre-lab activities, so you'll get actually the vast majority of the lab report done, hopefully tomorrow in class. Okay, and then on Wednesday, we have a shortened period, so we'll work on some other stuff that day, and then we will do the lab on Thursday. Okay, so your quiz, as always, will post between 3:20 and 3:30 today with the solutions video. It's going to be on properties of compounds from Friday and some naming stuff. Okay, so have a look at that tonight. Go over your notes from lesson 4. That was Friday's lesson. Go over those in detail because that stuff is going to be on the quiz. Okay, questions? All right, good work today, guys. Hey.